directions for Bohr's atomic model. So Bohr's solar system modeled the atom. All the planets are attracted to the sun by gravity. The reason that the Earth doesn't just float out into space is because it is constantly attracted to the sun. Similarly, the moon is attracted to the Earth by Earth's gravitational pull. So all of the planets are attracted to the sun, but they never collide with the sun. Negative charges are attracted to positive ones. Therefore, the negative charges, or the negative electrons in an atom, are attracted to the positive protons in the nucleus. In the early 1900s, scientists were looking for an explanation to a curious problem with their model of the atom. Why don't atoms collapse? The negative electrons should collapse into the nucleus due to the attraction between the protons and electrons. Why doesn't this happen? Scientists were at a loss to explain this until Niels Bohr proposed his solar system model of the atom. So again, they were kind of concerned. They knew protons had a positive charge and electrons had a negative charge, and they couldn't figure out why the atom just wasn't collapsing. So Bohr's reasoning. Number 1, consider swinging a rock on the end of a string in large circles. Even though you are constantly pulling on the string, the rock never collides with your hand. Why is this? So you can kind of replicate this if you have a lanyard. If you put your keys securely on the end of your lanyard, you can kind of swing your lanyard with your keys on it, right? And we know that as long as you kind of keep swinging your lanyard, those keys keep swinging. However, if you slow down, those keys stop making that circular motion. So the reason for this is that the rock must move quickly so that the pull from your hand isn't enough to pull the rock into your hand. Okay, and if you can go and swing your lanyard around outside away from your house with your keys on it, when you're swinging it around, let it go. When you let go, that lanyard heads off in a straight line path until gravity starts to act on it. Okay, so again, it's because realistically that the rock is moving very quickly. You're swinging it quickly, or you're swinging your keys quickly. Question number 2. Even though the Earth is attracted to the sun by a very strong gravitational pull, what keeps the Earth from striking the sun? Well, we know the Earth is on an orbit, right? And it's moving through that orbit pretty quickly. So really what's happening here is the moon, or the Earth, is constantly trying to get away from the sun, and the sun's gravitational pull keeps pulling it back. And that constant pulling it back as the Earth tries to escape the sun, okay, is what causes that shape. So what keeps the Earth from striking the sun? The fact that the Earth is moving quickly and constantly trying to follow a straight line path. Okay, unfortunately, it can't follow that straight line path because, again, the gravitational pull of the sun keeps pulling the Earth back into that circular or elliptical orbit. Okay, so again, the person who wrote this, the answer they had for number 1 was, the rock must move so quickly that the pull from your hand is not enough to pull the rock into your hand. If you were to let go, it would fly away from you in a straight line. The pull from your hand keeps the rock near you, but because of its initial velocity, it doesn't get closer to you. For number 2, okay, the fact that the Earth is moving keeps it from striking the sun. The Earth would move away from the sun, but the gravity of the sun attracts it, causing a circular orbit for the Earth. Number 3, there is a gravitational attraction between the Earth and the Moon. Why doesn't the Moon ever strike the Earth? Same reason, okay? The Moon is moving quickly, okay, and constantly trying to follow a straight line path. And again, it's that Earth's gravitational pull on the Moon that keeps pulling it back and giving it that circular or elliptical orbit. So question number 3, the person who wrote this explained it. The reasoning is the same as that for questions 1 and 2. So keeping in mind the planetary motion and attractions between planets and the sun, explain how it could be possible for electrons to not collapse into the nucleus. Well, again, the rock doesn't collapse because it's moving quickly and trying to go in a straight line path. The Earth doesn't collapse into the sun because, again, the Earth is moving quickly and always trying to go in a straight line path. And the Moon doesn't collapse into the Earth because the Moon is moving quickly and constantly trying to escape into a straight line path. So guess why it is electrons don't collapse into the nucleus? Okay, so the electrons are moving quickly, and they're constantly trying to escape the pull from the protons to follow a straight line path. Okay. The person who wrote this explained it this way: the electrons must be moving in orbits so fast that the pull from the nucleus is not enough to attract them towards the nucleus. This is Bohr's solar system model of the atom. All right, so talking about energy levels here. After Bohr proposed the solar system model, that electrons orbit a nucleus just like planets orbit the sun, he called the orbits energy levels. Consider the following Bohr model of a certain atom. So the white circles are protons, the black are electrons with a negative charge, and the neutrons have no charge and are kind of the grayed in ones. We see the first ring, which is our first energy level, and then the second ring, which is our second energy level. There are limits on the number of electrons that are allowed to occupy each energy level. In the first energy level, there can only be 2 electrons. Okay, so first energy level, 2 electrons. The second energy level is larger. It can hold 8 electrons. The third and fourth can hold more than 8, but we won't think about those limits yet. Okay, so number 5. In the preceding information section, there is a Bohr diagram of an atom. Which atom is it? So how do we know what atom this is? Remember, what makes one atom different from another atom is the number of protons it has. This atom has 3 protons. So then what we do is we consult our periodic table and we look for what element has atomic number 3. Okay, so this is, because remember our atomic number is our number of protons, so this atom is lithium. So the atom has 3 protons, so its atomic number is 3, therefore it's lithium. Okay. So question number 6. Draw a Bohr diagram for the following atoms. Note, before you can draw an electron on the second energy level, you must first have 2 electrons in the first energy level. Before you can draw an electron in the third energy level, you must first have 2 electrons on the first energy level and 8 on the second. The first one is done for you. So kind of let's talk a little bit about what this is. This is sulfur. Okay, now to know how many electrons we're going to have, remember we're going to look at sulfur's atomic number. Because this is a neutral atom, the number of protons and the number of electrons are the same. So sulfur, because its atomic number is 16, is also going to have 16 electrons. So again, we start with our first energy level and we see 2 electrons. Then we have 1, 2, 3, 4, 5, 6, 7, 8 electrons in our second energy level. And then that gives us 10 total, 1, 2, 3, 4, 5, 6 electrons in our third. So when we take a look at carbon, carbon is atomic number 6. That means it has 6 protons. It also has 6 electrons. Okay, so I'm just going to write 6 protons. So I remember that I have 6 protons in my nucleus. Here's my first energy level, and again, how many electrons can I put in the first energy level? Only 2. It does not matter where you draw the electrons. Here's my second energy level, right? I have 2 of my 6 electrons so far, so I have 4 left to go. My second one can hold up to 8, so all 4 are going to be in this second energy level. So I have 1, 2, 3, 4, 5, 6 electrons. All right, next we have sodium. Sodium is atomic number 11. That means it has 11 protons and 11 electrons. So sodium is going to have 11 electrons. So again, I'm going to draw my 11 protons, kind of like this, a P with a plus sign. And in my first energy level, again, I can only put 2 electrons. So that leaves me with 9. Remember, my second energy level can only hold 8. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 10 total. So I need a third energy level with just 1 electron. Lastly, we have phosphorus. Phosphorus is atomic number 15. That means it has 15 protons and 15 electrons. So phosphorus is going to have 15 electrons. It's also going to have 15 protons in its nucleus. So again, here's phosphorus's first energy level, and remember that one can only hold 2. Here's my second energy level, and it can only hold 8. All right, so that gives me 10 total so far. So I need 5 more, and this one can hold more than 8, so all 5 of them are going to be in this third energy level. So there's my Bohr diagram for phosphorus. All right, information about light. You may be surprised to learn that the behavior of light gives us some clues about the electrons in an atom. Before we can dive too deeply into it, let's recall a few things about light. First, it is a wave. White light is composed of all the colors of light in the rainbow. All light travels at the same speed, c, which is 3.00 times 10 to the 8th meters per second. The speed of all light in a vacuum is always equal to 3.0 times 10 to the 8th meters per second. Different colors of light have different frequencies and wavelengths. The speed, frequency, and wavelength of light can be related by the following equation. C equals frequency times wavelength. It is important that the wavelength is always in meters. The speed is in meters per second, and the frequency is in hertz. Note, 1 hertz is the inverse of a second, so that 1 hertz equals 1 over second. Okay, so that's some information we're going to use to answer some of our next questions. So I'm going to just kind of jot that equation so we remember it. And that C equals 3.00 times 10 to the 8th meters per second. Okay, that was kind of what we got out of this. Okay, and we also were told that we need our wavelength to be in meters, and we need our speed to be in meters per second. Okay, and frequency will be in 1 over seconds, which is a hertz. Okay? So, as the frequency of light increases, what happens to the wavelength of the light? This is a really common SAT type question. So what this is doing is, and a lot of times on the SAT, they're going to give you numbers with this. And you're going to spend time wasting your time putting numbers in. The key to this is, if I want to know about a relationship between frequency and wavelength, what I want to do is I want to take this equation and I want to manipulate it so that frequency and wavelength are on different sides, right? So C equals F wavelength. If I want frequency all by itself, I'm going to divide both sides by wavelength. And so my frequency is C over wavelength. Notice it doesn't matter. If I did it the other way, if I got wavelength all by itself, I would divide by frequency. And I would get wavelength equals C over frequency. Notice, either way I do it, the two variables I'm curious about are one's in the numerator of a fraction, right? Because I could technically write this as being over 1. And the other one's in the denominator. Anytime I have my variables and one's in the numerator and one's in the denominator, that means it's an inverse, okay, relationship, or it's inversely proportional. Now, you should have learned about what it means to be inversely proportional in math class at some point, right? That means that as one variable goes up, the other variable goes down. So these kinds of questions on the SAT, they often give you numbers, and they are trying to trick you into wasting time plugging the numbers into an equation and seeing what the answer is. If they give you the equation, all you have to do is manipulate it for the two so they're on opposite sides of the equation. If they're like this, they're inversely proportional. If they were both in the numerator or both in the denominator when I did this, then they would be directly proportional. Okay? Number 8. What is the frequency of light that has a wavelength of this? So they are asking us to solve for frequency. So my equation for frequency is C equals C, or frequency equals C over wavelength. C is 3.00 times 10 to the 8th meters per second. The frequency they gave me, or the wavelength, I'm sorry, is 4.25 times 10 to the negative 8th meters. Now, again, we have, if I just look at my units for a moment, I have meters per second divided by meters, which is the same as multiplying by its reciprocal. So notice I'm going to be left with 1 over seconds or a hertz as my unit, which makes sense. Now, let's talk for a moment, and we will talk more about this next trimester, but let's talk for a moment about how to put scientific notation into your calculator. Hopefully you've used this button right here, this EE button. So to put this in my calculator, I'm going to do 3, and that's a shift E8, okay, divided by 4.25, a shift E negative 8. Okay, when I use that little E button, it's taking the place of the times 10. And so it's a lot quicker to put it in my calculator, which again is important on a timed test like the SAT. So I see my answer here, and I'm just going to go ahead and use 2 decimal places. So I get 7.06 times 10 to the 15th, okay, hertz. So let's take a look at question number 9. What is the wavelength of light that has this frequency? So our equation for wavelength is wavelength equals C over frequency. Again, C is 3.00 times 10 to the 8th meters per second. Our frequency is 3.85 times 10 to the 14th hertz. So again, I have meters per second, and I'm dividing by a hertz, which is a 1 over second. So I'm effectively multiplying by my seconds. Okay, so I'm going to be left with units of meters, which makes sense. And then again, to put this in my calculator, I'm going to do 3E8 divided by 3.85 E14. And I'm going to change my mode here into scientific notation. Okay, and again, with 2 decimal places, I get 7.79 times 10 to the negative 7th meters. Okay, I won't be asking you to do any calculations like this, but it is a good chance to make sure you understand how to use your calculator. All right, light energy and energy levels. Higher energy levels are further from the nucleus. For an electron to go into a higher energy level, it must gain more energy. Sometimes the electrons can absorb light energy. Recall that different colors of light have different frequencies and wavelengths. If the right color, and therefore frequency, of light is absorbed, then the electron gets enough energy to go to a higher energy level. The amount of energy and the frequency of light required are related by the following equation, E equals hf. E is the energy measured in joules, F is the frequency measured in hertz, and H is Planck's constant in units of joules per hertz, which is the same as a joule second. Planck's constant H always has a value of 6.63 times 10 to the negative 34th joule seconds. An electron that absorbs light energy and goes to a higher energy level is said to be excited. If an excited electron loses energy, it will give off light energy. The energy and color of light depends on how much energy is released. Again, the frequency and energy are related by the above equation. When an excited electron loses energy, we say that it returns to its ground state. Since not all electrons start out in the first energy level, the first energy level isn't always an electron's ground state. We have a couple pictures here which are pretty important for us to take a look at. Right? We see the ground state of an atom, and we see 2 electrons in our first energy level and 1 electron in our second. The same atom is now in an excited state. Notice we have only 1 electron in our first energy level and 2 electrons in our second energy level. Both of these have 3 electrons, but notice where those 3 electrons are in the energy levels are different. So, taking a look at question number 10. If you are given a Bohr diagram of an atom, how can you tell if it is in the ground state or in an excited state? Again, remember when we talked about these Bohr diagrams, we said the first energy level would hold 2 electrons and that we needed to fill it up with 2 electrons before we put electrons into the second energy level, which could hold 8 electrons. Notice, this atom, the first energy level is full before I put electrons in the second. In this atom, my first energy level is not full like it needs to be. So, the question is, if you're given a Bohr diagram of an atom, how can you tell if it is in the ground state or in an excited state? Okay, it's excited if each energy level isn't full, right? Or doesn't contain the number of electrons it can hold. Okay? Again, the person who wrote this ChemQuest, and it wasn't me, okay, explained it this way. You will see an electron in an upper energy level before all the lower ones are full. So question 11 asks us to label each of the following atoms as ground state or excited state. And to do that, we're going to have to count how many electrons are in each energy level. So this first picture, we have 2 electrons, and then we have 3 electrons. Well, remember our first energy level can hold 2 electrons, so it's completely full. So this would be ground state. In our next one, we have 2 electrons in our first energy level. We have 1, 2, 3, 4, 5, 6, 7 electrons in our second energy level, and 1, 2 electrons in our third. Remember, first energy level is completely full like it needs to be. But remember our second energy level can hold 8 electrons and we only have 7. That means this atom is in its excited state. oops, which I spelled wrong. Okay. Okay, excited state, not exited state. All right, our last picture. 2 electrons in our first energy level. 1, 2, 3, 4, 5, 6, 7, 8 electrons in our second. 1, 2, 3 electrons in our third. Again, our first energy level is completely full. It's holding its 2 electrons. Our second energy level is completely full. It's holding its 8 electrons. So this is in the ground state. 12. Does an electron need to absorb energy or give off energy to go from the second to the first energy level? So if we're going from this higher energy level to a lower energy level, would the electron need to absorb or give off energy? Right? It would need to give off energy. How is it possible for an electron to go from the third to the fourth energy level? So if to go from a higher energy level to a lower energy level, the electron has to give off energy, what's going to happen for an electron to go from a lower energy level to a higher energy level? Right? The electron will need to absorb energy. Okay, so to go from a higher energy level to a lower, we're going to give off. To go from a lower energy level to a higher energy level, the electron's going to absorb energy. Number 14. Red light of frequency this is required to excite a certain electron. What energy did the electron gain from the light? Okay, that wants us to use this equation back here, the E equals HF. So we have E equals HF. H was a constant, right? It's right here, the 6.63. Okay, so 6.63 times 10 to the negative 34th joule seconds. Okay. F is 4.37 times 10 to the 14th, 1 over seconds. So again, I have joule seconds times 1 over seconds. Notice my seconds are going to cross out and I'm going to be left with joules, which makes sense for energy. And again, on my calculator, okay, I'm going to take 6.63 E negative 34 times 4.37 E 14. Okay. And I get, okay, with 2 decimal places, 2.89, or 2.90 we'll say. 2.90 times 10 to the 19th joules. The energy difference between the first and second energy levels in a certain atom is this many joules. What frequency of light is necessary to excite an electron to the first energy level? So they want frequency, so we're taking our E equals H frequency, and we want to solve it for frequency. So divide each side by H, so frequency equals E over H. My energy is 5.01 times 10 to the negative 19th joules. Okay, my H is still the 6.63 times 10 to the negative 34th joule seconds. Right, my joules are going to cross out and I'm going to be left with 1 over seconds, which is the same as a hertz. Again, to put this in my calculator, 5.01 E to the negative 19th divided by 6.63 E to the negative 34th. And again, I'm going to use 2 decimal places, so I get 7.56 times 10 to the 14th hertz. Number 16. What is the frequency of light given off by an electron that loses this many joules of energy as it moves from the second to the first energy level? So this is again asking us the same kind of question. So again, the energy they gave me was 4.05 times 10 to the negative 19th joules divided by 6.63 times 10 to the negative 34th joule seconds. I'm going to be left with a 1 over second or a hertz. Okay. So 4.05 e to the negative 19th divided by 6.63 e to the negative 34th. And I get 6.11 times 10 to the 14th, okay, hertz. What wavelength of light does this correspond to? So they want us to figure out wavelength here, right, which is C over our frequency, which is what we just calculated, okay? So remember our C was 3.00 times 10 to the 8th meters per second divided by the 6.11 times 10 to the 14th, 1 over seconds. So we have meters per second divided by 1 over seconds, which is the same as multiplying. So I'm going to be left with meters, which makes sense. Oops, too many ups there. Okay, so I'm going to take 3e8, and I'm going to divide it by my answer because my answer is still stored in my calculator. Okay, and so I have 4.91 times 10 to the negative 7th, okay, meters. If all of the electrons in atom A get excited and then lose their energy and return to the ground state, the electrons will let off a combination of frequencies and colors of light. Each frequency and color corresponds to a specific electron making a transition from an excited state to the ground state. Consider an atom from element B. Would you expect the excited electrons to let off the exact same color of light as atom A? Why or why not? Okay, so hopefully as you kind of think about that, you realize that it shouldn't give off exactly the same color of light because it's going to have a different number of electrons, and therefore it's going to have a different combination of energies and of colors of light, and those different energies and colors of light are going to combine in different ways. So no, since atom A and atom B have different numbers of electrons, their overall frequency and therefore color of light will be different. So I hope that helps you. If you had some questions about this chem quest, have a great day. I'll talk to you tomorrow.